So, in this module what we will do is, the aim of this module is to tell you about some simple methods which will allow us to solve another class of second order differential equations which are known as Schrodinger equations. So, what this we will do in one dimension. So, the aim is solve one dimensional Schrodinger equation using the Numerov algorithm. So, we are all aware of what a Schrodinger equation is, but just for the sake of completeness I am writing it down once again, minus h cut square by twice m d2 psi dx2 plus v as a function of x, psi is also a function of x here, equals to E psi x. So, this is my 1D Schrodinger equation. So, if you look at it, that this is again nothing but a second order differential equation, and you have learnt already in the previous modules how to handle it, but there are some other additional complexities to this system, while that is the reason why it needs some special treatment. So, we will talk about that. So, the focus here is sort of to get. So, what you get if you are able to solve the Schrodinger equation analytically, you get a spectrum of discrete eigenvalues. For which there exists a unique eigenfunction. So, our aim is to obtain these eigenvalues and eigenfunctions numerically, because in most of the practical cases we will not be able to solve this Schrodinger equation analytically. So, in this part of this course, what we will learn is, we will learn for the special case of 1D Schrodinger equation, and the algorithm which we will discuss is known as the Numerov algorithm. And then what we will do is, we will take an example, and the example will be basically my 1D quantum mechanical simple harmonic oscillator. So, this is the plan of what we are going to cover in this part of the course. So, but before we go into these two parts, that is, before we talk about the Numerov algorithm and before we talk take a practical example and apply the Numerov algorithm. So, what I would like to discuss is now the problems, the additional problems which one typically faces when one solve this type of two differential equation, for particularly in the area of quantum mechanics. So, one issue is already there, is that you do not know how to do the integration analytically to get the solution, that is how I mean what is the function as a function of x. So, for that the Numerov algorithm is already there, which we will see, but in addition to that there are two more problems which are associated in solving this type of Schrodinger equation, particularly in the context of quantum mechanics. So, basically, so it will be more like a sort of an overview. So, what we are going to talk about is quantum mechanics and the issues with numerical codes. That is, what are the additional challenges and complexities. Primarily, there are two types of additional challenges and complexities which one come across here. The first complexity, which is pertain to the fact that when we solve a quantum mechanical Schrodinger equation, what we end up at the end of the day is discrete set of eigenvalues. Which I am calling as E n. Note that in my Schrodinger equation, if I just write it down here, and so that we have it with for our reference, d2 psi dx2 plus Vx psi. So, psi's are function of x goes to E psi x. So, one of our unknowns is this quantity, which is my psi x. In addition to that, we have another unknown, which is E n. So, we do not know what the energy eigenvalues are. So, we only know that these are a set of discrete energy eigenvalues. So, hence both E n and psi x both are unknown here. What we know is that the fact that for each E n we have a solution psi n. And another important fact is, but the complexity lies in the fact that there is only certain eigenfunctions which are there are only certain psi n which are allowed based on the type of the problem and the boundary conditions we are applying. So, only certain psi n, sorry, this will be x, are allowed. However, if you solve this numerically, so numerically any psi n are maybe a solution to my problem. Numerically any psi n can be a solution. But that solution may not be physically correct. They not be given because we should remember that psi the wave function of a particle, the one physical interpretation of the wave function of the particle is that it gives me a probability of finding a particle at a given position x. So, if once we know the wave function, we can find the probability of the particle at a given position x. So, what this particular statement means that numerically any psi n can be a solution is that we might end up in a unphysical solution where the wave function may diverge. For example, if we are in the position space, if we are at a point where classically the wave function is forbidden, or classically the particle is forbidden to stay there. So, from a classical picture, it is impossible, the probability of finding the particle there at that particular point is 0, but quantum mechanically what you would expect is, because of the tunneling phenomena, there is a finite probability of finding the particle. So, the wave function at that point, the correct physical behavior of the wave function is that it should diverge, it should decay exponentially to 0 at that point in the space. But there might be possible that there is another numerical solution, which is another numerical wave function the code can find, where instead of its decaying, it just simply diverge at that point. So, so this is the complexity which one of the complexities which I am talking about for these type of using codes for quantum mechanical methods. So, when we write a code, what we need to keep in mind is the following things. So, basically your numerical code should be able to do the following things. So, first of all, it should recognize the fact that we discussed above. It should recognize that all psi n's are not solutions, are not allowed solutions, which in other word means that it should be able to identify the correct values of E. Only if it identifies the correct value of E, then only can it identify the correct corresponding solution. And in order to do so, what it should be able to do is, it should be able to search for a better energy until it coincides with the exact solution. So, remember here I am using exact within quotes, in the sense when I say exact, I mean exact within the numerical accuracy, because numerically we will, in most cases we will never get numerically we will, in most cases we will never get the exact solution. We can be close to the exact solution, because there will be always some numerical errors present with the same. So, this is one problem, and second problem, it is a sort of a, one can say that it is a pathological problem in quantum mechanics, is that it has a pathological asymptotic behavior. So, what do we mean to by that? So, by the statement that in the problems in quantum mechanics have a pathological asymptotic behavior. So, what I am really trying to point out is to the fact that in quantum mechanics, unlike classical mechanics, it is possible to have negative values of kinetic energy. So, what I mean is, it is possible to have negative values of kinetic energy. So, when this is possible? So, this is possible when my potential, say potential at a given point x, is greater than the energy of the particle. So, how this is possible? So, we will let me just explain to you by taking a simple example. So, let us assume that my potential V x is a constant, and let us suppose it to be V. So, if I write my Schrodinger equation, so what I have is minus h cut square by twice m d2 psi, which is a function of x dx2 plus, now my V is a constant here, psi x, this gives me E psi x. So, this is my Schrodinger equation, and if I want to compute the kinetic energy, what we need to do is, we need to compute the expectation value of my kinetic energy operator, which is nothing but h cut square by twice m d2 psi x dx2. So, this is nothing but, so what I do is, I will call this as my kinetic energy operator. So, what it means is, basically we need to evaluate this term and integrate it over the x here, because it is a one dimensional case. Now, in order to evaluate this term, what we can do is, we can take the help of this Schrodinger equation here, this one. So, from here what we see is that the kinetic energy operator, sorry, the psi x won't be here. So, this is my operator. So, what we can see here is d2 dx2 psi x, this we can write as E minus V psi x. So, what we will do is, so basically in this integral, this term we will replace with this particular term here. So, if we do that, so what we land up with is, we have psi star psi E minus V psi dx, and this E is also a constant, V is also a constant for us. So, we can pull that out. So, we will get this quantity, and assuming that my chi's are normalized, the integral. So, integral over chi star chi dx will be equal to 1. So, this is what we will be getting as the expectation value of my kinetic energy. Now, if we go back to the beginning. So, we were talking about this V x greater than E. So, my V is greater than E. So, what this implies is that my kinetic energy, which is given by this term E minus V, this will be negative. So, in this case we have a negative value of the kinetic energy. So, now if we try to find the solution of this, so what we can do is the following. We can write it in a simplified form. So, what we can do is we can write the Schrodinger equation again in this simplified form, where if I go back here. So, what I am doing here is I am taking this term on this side, and then this term also on the right hand side, and then rewriting the equation again. So, what I will get is minus twice m by h cut square E minus V psi x. Okay. Now, if I look at this carefully, so this term in the bracket E minus V, this is a negative term, and we have a negative sign here. So, this whole term here, so this whole term, the coefficient here we have, this is a positive quantity. So, what I can do is I can rewrite as k square psi x. So, my Schrodinger equation, what I am doing is I am rewriting it in this form, k square psi x. Now, this type of equation we have already seen earlier, and the typical solution. So, there are two possible solutions of psi x. So, one is my psi x is approximately equal to e to the power minus k x, or my psi x can go like e to the power k x. Now, the condition that my V is greater than E. So, this implies in the classical picture. So, classically what we have is that it's the particle is forbidden to be there. Which in other words implies that the probability of finding the particle is at that place, at that value of x, at those values of x where V is greater than my this E is equal to 0. But quantum mechanically we know that it is possible to have this tunneling effect. So, what you will expect the wave function to behave like is it will have a exponentially, it will decay down to 0 instead of abruptly going to the 0 value. So, the physical picture is the correct physical picture, which or the correct physical solution in this case will be this one, where my wave function decays exponentially to minus x. But this we can look at the equations and tell that okay, this equation, this particular equation is my physical solution, while this is unphysical because here it is diverging exponentially the wave function. But when you are trying to numerically solve it, neither the code nor the computer understands this fact. So, that gives rise to the lots of problems, and so the idea is your code should be able to identify numerically the physical solution. The reason for this is that even if during when you are evaluating or solving this differential equation, although if there is so what you are doing is basically you are doing integration. So, when you are doing integration, the problem is if there is a slight amount of numerical noise. So, usually what happens is that it gradually builds up and then your solution blows. So, what you might see in these type of problems, if you do not take care of these facts, that you say for example, in this case your wave function should decay exponentially. If you do not take care while writing the program to enforce these facts, what will happen is that in the classically allowed region you may get the correct solution, while you will while in the classically forbidden region your solutions might diverge. So, we will see when we will do the example of the Schrodinger equation, how I mean how if we do not take care of this particular aspect of the quantum mechanical problem, how you can end up wrong diverging solutions or wrong diverging wave functions in the classically forbidden region, although you might not find anything any problem in the quantum mechanically allowed region. So, the idea is you should have a code which will sort of take care of both these two aspects associated with the quantum mechanical problem. The first aspect is that you have discrete energy eigenvalues and only certain eigenfunctions are allowed, which are determined by the boundary conditions which we allow to the problem which we are solving. And the second fact is that in classically forbidden region, the wave function should decay exponentially to 0. So, the asymptotic behavior. So, this is nothing but the second point is the asymptotic behavior of the wave function at large values of x, how it should behave for a given particular function. So, this behavior also should come out, the code should able to come out with solutions with the correct asymptotic behavior also. So, both these facts needs to be taken care of when we are trying to solve quantum mechanical problems numerically. So, with this brief introduction of the issues associated or the additional difficulties associated with solving quantum mechanical problems numerically, now what we will do is we will move to the Numerov algorithm. So, I will briefly derive the Numerov algorithm for this, and then what we will do is we will apply this Numerov algorithm to solve the or to find out the eigenvalues and eigenfunctions of a quantum mechanical 1D simple harmonic oscillator.